First of all, let's talk about an internal combustion engine. That's how to start this chapter. We'll talk about the 4-stroke cycle. There is a 2-stroke cycle. It's worth looking at. Whoever came up with the 2-stroke cycle was a genius, in my opinion. I don't know. But it's really a great cycle. Unfortunately, it has higher hydrocarbon emissions. So it's on the decline in most of the industrialized world because we want to have cleaner emissions from our engines. So the 4-stroke cycle's out there. But there's a lot of 2-strokes when you want a very lightweight, high power engine on a boat, right? And also on little itty-bitty aircraft. If you're a model airplane flyer, that's all 2-stroke. Weed eaters, hand tools. Now the lawn mower is typically a 4-stroke, although there used to be, and I don't know if there still are, some 2-stroke push lawn mowers out there. All right. Typically, what you tell is, do you have to add oil to the gasoline? True. If you add oil to the gasoline, that's an indication that it's a 2-stroke. And also, what's interesting about 2-strokes, some of the biggest, the largest, the most humongous engines out there that are reciprocating piston cylinder engines, internal combustion engines like that, are 2-stroke. So they cover the low end, and then they cover the high end, which is very interesting. All right, so then we'll talk about how we analyze really complicated systems. And the way we analyze them is we make some assumptions. We make some simplifying assumptions so that we can do some calculations equipped with the tools that you've already learned so far in this class, which is a major accomplishment, to be able to analyze something close to the real world with a number of simplifying assumptions. So then we'll do the Otto, gasoline, diesel, like diesel fuel engines. So Ottos have spark plugs. There are no spark plugs in a diesel engine, true? There are glow plugs if you want to start on cold days, but they're not spark plugs, and they don't have the purpose other than to get you started. Glow plugs only get you warmed up to get started on cold days. Then we'll talk about gas turbines for power production, especially to turn a shaft and make electricity. There's a lot of electricity generation using natural gas in the United States and Texas. And then also just to turn a shaft to do some work. A lot of gas turbines are used for propulsion systems. Basically for aircraft propulsion, you don't turn a shaft to produce power there. A lot of times an aircraft that's thrust out the back. But if you're flying a helicopter, a lot of helicopter engines are gas turbines. They're not reciprocating. They're gas turbines. If you're in a ship, you're in a Navy vessel, Coast Guard, you want to really move, it's a gas turbine. Or if you're a huge aircraft carrier, you're a nuclear power plant with the vapor power cycle that we studied, the Rankine. So you're going to find gas turbines out there in a lot of places, and the gas turbine industry has been booming for the last 10 or 15 years. A lot of money and a lot of jobs and a lot of high-end engineering jobs, because this is a very complicated device, the gas turbine. So we'll just get the brief introduction to it. It's really the domain of mechanical engineers. It's not the domain of civils or electricals, etc. It's really the domain of mechanicals. So we want to be able to talk about pistons, cylinders, spark plugs. So we have a cylinder, and this is a very crude sketch. It will have a piston that slides back and forth in the cylinder, and when it's up at the top, it's at top dead center, and then it slides back and forth and goes down to a bottom dead center, top dead center. So that's our first concept, is a piston in a cylinder. And then typically in the gasoline engine, you have a spark plug, some device that will have a gap, and across that gap with a large voltage jolt, I forget how many thousands of volts, 10,000, 20,000 volts. There'll be a little spark that'll cross that gap, and it'll start the combustion process when the engine or the design engineer is controlling and designing that engine, sends a spark to that spark plug, right? High voltage pulse. It's the way you have the piston connected is through a connecting rod that goes down to a crank that has an offset. Now I'm really probably going to botch this, so let me try and draw it like this. I'm going to put it like this, come down like that, and then here's my, that's going to really botch it anyway. There's my center of the crank, which is rotating, and when the connecting rod, that's this red part, it's connected to the piston and it's sitting up at the top, then it's there. But if this rotates and rotates and rotates and rotates and rotates around, then it's down here, then the connecting rod connects there. Okay? Then if it rotates around to here, maybe the piston is halfway and the connecting rod is connected there. So what you have is you have reciprocating motion, sliding back and forth, up and down inside the cylinder, reciprocating motion, and it's translated into rotary motion in the crank through that offset. Well, a picture is worth 1,000 words. Don't you think that picture is a great picture? Isn't it worth 1,000 words? I see an honest student out there shaking his head. That's a terrible picture and it's not worth 1,000 words. But what you can do is you can flame off to the internet. And you can just do Wikipedia search on internal combustion engines. The beauty of this is you get dynamic. So here's an image of a piston sliding up and down and how you have that offset with the crankshaft. Now everybody's in here an aspiring mechanical engineer. This is one of these top 10 inventions of the world of all times. The internal combustion engine. It did. I mean, somebody made a list of what's the top 10. And yes, they had some civil engineering things like clean water, wastewater, toilets. I'm so glad we have sewer systems. That is top 10. Let's leave it in the top 10. But also, there's gas turbines and reciprocating engines. So if you've never seen a dynamic like this, a motion, how that translates, you should do that. And then what do we have? At the top, we have a rotating device. Can you see it rotate and it goes around? That's called the camshaft. And then it's pushing on a lobe. Can you see it has a lobe on one side? Over here is another camshaft. It's a dual overhead cam. How do you like that, huh? So, and then you have, it's going to come around and push down. When it pushes down, this is a particular valve. It's a poppet type valve, spring loaded right here, and it pushes down and it comes off of the seat and it opens up a ring for flow around that valve, a gap. That's circular, a ring type of gap, okay? And so it can flow into the chamber as the piston's coming down. That's one. As it going down, just get one first. So it's ingesting this nice blue as it goes down. Then at the bottom, that valve closes and this compresses and goes up. I really can't slow this, at least I don't know how. And as it goes up, that piston's got the first stroke down, second stroke up. And it's compressing it. Both valves at the top are closed. One's the intake. It was open on the intake stroke coming down. Intake valve closed, and both exhaust and intake valve are closed. You have an upstroke called the compression stroke. At the top, you see a little pop on the spark plug, boom. And then, here it goes, right there, boom. Now it's a high pressure, high temperature gas because it's exploded or burned, rapid combustion. And it's going to spank the top of that piston down. Push, 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 very high pressure, pushing that piston down. That's your power stroke. Okay? Why is it so high pressure, high temperature? It was a rapid release of thermal energy due to the combustion of the air-fuel mixture. The spark started it, and boom, it burned it. Then you have expansion coming down. That's the power stroke. Then at the bottom, the exhaust valve over here opens, and you have an exhaust stroke going up, pushing out the exhaust gas products. The products of the exhaust combustion, the combustion going out. Now the other thing is when the piston's expanded, it's not expanded all the way down such the pressure in there is back to 100 kilopascal or ambient pressure, and then the exhaust valve opens and nothing leaves until the piston starts pushing up. No. It's high pressure still. And when that exhaust valve cracks open, there's a Mach 1 rush of gases because there's a very high pressure difference across the opening, and you get a loud noise. It's a very loud, that's why you have mufflers. So those are the valves. Did I cover everything? The spark plug, you have the intake, you have the exhaust. And now how many strokes do you have in a 4-stroke cycle engine? Can you list them? It really doesn't matter what order you come in. You have the intake stroke, compression, power, exhaust. Okay? How many revolutions of the crankshaft have to go for one complete cycle? 2. It's very tricky. You got to learn that, right? Because you have a half of a revolution on each stroke. So as you come down from top dead center to bottom dead center, that's the intake. Bottom dead to top, compression. Top to bottom again, power. Bottom to top, exhaust. All right? And these illustrations are really good. Let me see if there's any other dynamic illustration. This is the 2-stroke. Whoever did it, again, I think is absolute genius. You look at it and figure it out. Why do you put the oil in your gasoline mix for a 2-stroke? Lubrication. This is incredible. This is a really good engineering device. You know who did a 2-stroke? I have no idea. We should find out who did it first and then attach their name to it. Call it the Otto cycle, call it the diesel cycle, call it the Brayton cycle, call it the whatever name of this person who did it cycle. All right. Let's jump on back to my illustration. So what is the bore? We already have the connecting rod and the crankshaft, the spark plug, the piston, the cylinder. What's the bore? The bore is the diameter. It's the diameter of the piston in the cylinder. Now, isn't there a little difference in the bore, maybe the diameter of the piston, diameter of the cylinder? They're so tight, nobody cares. Not that I know of. Of course, there has to be a little gap, right? And they seal it with rings. They typically have 2 compression rings and an oil ring to help sweep it, the cylinder. On these, they could have more. The stroke is the distance moved from the top of the piston as it goes from top dead center to bottom dead center. Well, why don't you do the bottom? Okay, do the bottom of the piston. Anywhere, middle of the piston, something. But it's the distance slid. Okay? So now, if you have that distance slid from top dead center to bottom dead center, you have what they call the displacement volume. So the volume displaced is equal to the stroke times the area, which is pi bore squared over 4. B is the bore, stroke is S. And then when the piston's at top dead center, often we have, thanks to Chrysler's innovation, what kind of engine did they first come out? Chrysler, Mopar? The Hemi. And so what did they do? They got rid of the flat head. They got a hemispherical head. Really innovative design at that time. I don't remember what year, but 50-something. I think 54, 52, I don't remember. Well, it's the spark then more goes out as a spherical pattern, and you had a slope to help ingest things so that it was turning and coming in, and then turning and going out smoother, less 90-degree turns on the intake and exhaust. Yeah, but it used to be, what did they have, a flathead? The piston, the cylinder went up here, and didn't they have the spark plug over here, and this was like the combustion chamber? Talk about 90-degree turns of the fluid. Anybody taken one of those engines apart? It's been a long time since I've seen one. Didn't they call it flathead? Flatheads. And they drove many engines through many years in automobiles, right? So you could probably do a Wikipedia search, and we could do that too and find a good image of that. But there's my rendition. And then, so the compression ratio, this book uses the symbol R, just R, lowercase r, as a compression ratio, is this volume, how much you start at the bottom dead center. If you start at the volume at bottom dead center, that's large. If you go to top dead center, it's small. This doesn't go to 0. This goes to your clearance volume. That's this volume inside, let's say, a hemispherical part. And then what about at bottom dead center? Well, you still have the clearance, but you also have the displaced volume. And so a lot of these engines will be characterized by their performance. Let's say, what is your bore? What is your stroke? What is your displacement per cylinder? Or if you have 8 of them, then they give you their displacement for the whole engine. And then they have the compression ratio. So how many people know the displacement of their whole engine? If they have a 4-cylinder, 6-cylinder, 8-cylinder, how many people know of any engine they own in a vehicle? One. It's the liters of the engine. So how many liter engine do you have, or a cubic inch? A 3-liter, 3.0 liter. So you also had one. What do you have? A 6.0 liter? That's big. Is that a diesel or gas? It's a V8 gas? Okay. Who puts it out? Chevys. All right. Yes. 1.376. So his 1376 cc, typically motorcycles are quoted as cc's, or a 1.376 liter. Is that a motorcycle? Yeah, pretty small. I think the smallest I've seen, on a car, little itty bitty Hondas that really go down there. I'm trying to remember the smallest Honda engine. Anybody know in a car? 1.8? About 1.8? That's pretty small. Oh, really? Now they started going away from 4, they went to 3 cylinders, and I don't know what some of the 3-cylinder car engines are anymore. They're what? The Geo is a 3-cylinder? Yeah, but I don't know the displays. But typically they used to all be 8. You had to have an 8. And then I don't know what happened to the price of gas. It changed people's opinions. You don't need the 8-cylinder anymore. I don't know why. But then it went to 6s, and now a lot of people are happy with the 4s, right? When they fill up. That's me. Somebody else should know their cylinder size, their engine's displacement. What do you have? 5 liter? All right. Anybody thinking cubic inches anymore? The Chevy 350? The 350 what? Cubic inch? Cubic inch. All right. The 454, Chevy 454 cubic inch. That's what I was when I was your age. What do you have? 3.8 liter? Yeah. That's a 6-cylinder? Yeah. So anybody else want to? 3.7. I think my neighbor has an 8.2 liter. And when I popped the hood, I looked in there and I said, whoa. No wonder. It's a 4x4 Suburban built in 05 with it's a 3/4 ton chassis. I mean, the thing could pull 12,000 pounds. That's a rated capacity, pulling capacity. So it's a huge monster, but it does not like to pass gas stations. It likes to pull in. So that's your displacement volume. Now, what about compression ratio? Of those that gave me their volume, the size of their engine, how many people know the compression ratio in it? 8. 8.5? That's pretty low, actually. I thought maybe higher. Who else? 9.5? Okay, high performance. Do you have to put a special higher octane fuel? You have to put in the premium gas when you start pushing up into 10s and 11. So he has to be, you got 3 selections of gas. If you don't know what you have for your engine, go for the cheaper. True? But if you know that you have a higher compression ratio engine, then you are forced to put in a higher. Otherwise, it'll ping and not run worth a hoot. Right? Anybody know what I'm talking about? But an 8.5, low grade. It's what? Oh, it's turboed. Yeah, okay, it changes the game. When it's turboed, it changes the game. Yeah, you can't go at high compression turboed. Too much. Well, we're not going to talk about turbochargers. Anybody else know what their compression ratio is? So we got a range. A lot of them are in the 9-ish to 10.5-ish. And they were able to push those up over the years by better designs of engines to dissipate heat and to get rid of hot spots. You wonder why they went to aluminum heads? They could get up a little bit higher on the compression ratio, better for performance, with the lower grade gas and not have that hot spots, which would have multiple. The hot spots act like they're a spark plug. They're saying, I'm ready to combust. Let's go for it. So you have multiple combustion sources or locations going on. It's not good. So let's talk about a pressure volume diagram. We'll put what you have is a pressure volume diagram. You could put, let's do B. If you're at bottom dead center, don't you have the maximum volume? And then if you're at top dead center, don't you have the minimum volume? And so what your piston's doing is going through 4 strokes, okay? And we want to trace as realistically as possible what a pressure volume diagram would look like under a load when the engine's loaded. And then if you unload it, it would change the shape of this PV diagram. But let's start with down here, let's put atmospheric pressure as a reference. That's ATM, 1 atmosphere. Okay? And let's say you're at bottom dead center, you're right around here, and you start the compression stroke. Got it? You're going to do the compression stroke first. It's going to be coming up, go like that, get higher pressure, right? And then you get a kick. Typically the spark plug fires a little before top dead center so that the combustion can get going, and you're running this thing at thousands of RPM, 2,000 RPM, it's not that fast. You're idling at 750, 900 RPM. You have running down the road maybe 2,000 RPM. How many people have a tachometer in their car? Right? And so if you're driving that engine to Houston at 70 miles an hour on I-10 at steady state, what's your tach showing roughly? How much? Around 3,000, okay? Who else knows what their tach is showing if they're running 25, 2,600? All right, now let's go to the motorcycle. I don't like this when they throw out these numbers. Do you know what your idling? Okay, and then where's your red line on that motorcycle? 12,000 RPM. You don't even, you put your legs around that engine. How can you do that and then rev it to 12,000? I'm thinking of explosions at that point. But they really are very, very high RPM, right? How about yours? 7,000 RPM? Yeah. Harley, so it's a low, blah, 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 instead of one of these whining. Okay. So yeah, and so even in an automobile, I don't like to hear them go 4,000 or 5,000. They sound like, I like to baby mine. But my kids, whatever they get in the vehicle, they think that foot is, they just run it hard. Every vehicle I have, and every vehicle they have. Anyway, so this starts combustion, and the pressure really goes up dramatically, even though it's still compressing, but it's just near top dead center. Then it's at top dead center, and it's still going up, combustion still going on, and then it starts what stroke? The what stroke coming down? The power stroke. And before you get to bottom dead center, the exhaust valve will typically crack open right around here. And then they'll have a very rapid decrease in the pressure. Blow down. A lot of exhaust is trying to rush out. It's very loud. This is a loaded engine. Okay? So this is where the exhaust valve opens. This is what happened at this red star right here? Spark plug. Plug fired, and so you started combustion. All right? So then you have this, typically, essentially at bottom dead center, a very much a blowdown. Now it still has to be above atmospheric pressure as you go through the third stroke. The first stroke I forgot was and then power. Now we're going to go through the exhaust, pushing out some of those. There's a blowdown. A lot of the exhaust products have left, but you still have to have it above atmospheric pressure to have exhaust. Why? Because it's got to push it out through across the valve, a pressure drop, through the header, the exhaust manifold, then through the catalytic converter. You got two of them, great. Through both catalytic converters, through the muffler, through the tailpipe, and then finally, at the end of the tailpipe, atmospheric pressure. So it's all got to be pushed out. Excuse me. And then, as you get down here, what happens? Now you're going to go through the fourth stroke. You already had the compression, power, exhaust, intake stroke. And the intake stroke has to be less than atmospheric pressure because it's got to suck the air in across the air filter, which is typically not trivial, through the intake manifold and across the valve, the intake valve, and into the cylinder. This is the pressure in the cylinder that we're looking at. So that's all a vacuum, and there you go. So there's a loaded engine running. And you get, if you're expanding at high pressure, you have more power out than compression. So you want to open up this area. If you open that area up, you get more power out. So, right? And then if you are just sitting there idling, you're not really producing a lot of power, it's just self-sustaining, that purple shaded area will collapse down to minimum, just so it overcomes internal friction and just running it. So you can look at these PV diagrams when the engine's producing a lot of work or when it's just idling. What is the mean effective pressure? I'm not a big fan of it, but here it's defined as the net work for one cycle divided by displacement volume. And it's a metric. It's just another metric. Displacement, we say, oh, you have a 6-liter, engine. Ooh, that's big. Oh, a 1.6 liter engine. Oh, that's small. See, these are just metrics to help describe. Oh, 8.5 compression ratio. Without turbocharging, that's not much. With turbocharging, it is. But if you go up higher, 11 compression ratio, those are metrics for the engine. Now we're going to say, how can we analyze this using the tools that we've already learned in Thermo 1? So now we want to talk about air standard analysis. So we focus on a fixed amount of air that's trapped in the piston cylinder apparatus, and we never let it come in and out. We never let it come in and out. So it's always air. It's never converted to combustion products, so it's always that right nitrogen-oxygen combination. It's called air. And it's always an ideal gas. Three things: PV is equal to RT, U is a function of temperature only, and enthalpy is a function of temperature only for ideal gas. And then the combustion process is so complicated, we're going to approximate it by replacing it by a heat transfer that comes in. Now that heat transfer could come in at top dead center. Typically it's coming in when the piston's when it's trapped, it's a minimum volume, but we're going to do the Otto cycle, and then we're going to look at the diesel cycle. And they don't come in all at the same condition. One comes in for the Otto, constant volume at top dead center. The other is, it starts at top dead center, but constant pressure as you start to expand in the diesel cycle. There's no intake or exhaust processes. It's just pure air all the time. And the exhaust and intake are replaced by heat transfer out to get it back so you can start it again. All processes are internally reversible. And so why do we make all these simplifying assumptions? So we can make a calculation doable. And then if you add cold in front of this air standard analysis, that means everything in the above list, it's an air standard analysis. But the additional assumption, approximation, that you're going to use constant specific heats, and those constant specific heats are evaluated at room temperature, 25 C, at standard temperature, not a high temperature. And then why do we make this additional simplifying assumption? Is it because it's more accurate? No, it's not. It's less accurate, but it makes it even more doable. It makes it more where I can analyze a complicated system. So let's go ahead and review. What is our equations of state? PV is equal to RT and the different versions of it. If somebody says, I want you to calculate changes in internal, changes in enthalpy, and changes in entropy for an ideal gas, assuming or modeling with variable specific heats, how would you do it? How would you do that? To account for variable specific heats, you'd use table. The air table, true? What is it, A19 or something? The number of it really doesn't matter. This textbook will change another version. That'll be another table number, but it's around there. And you find that U at T2 minus U at T1, likewise H at T1, minus H at T2. Ugh, come on now, I can write final temperature minus the initial temperature, true? What about S? S at T2 naught minus S at T1 naught minus our natural log of P2 over P1. How many people forgot and missed the first question on the exam because of this term? The entropy not only changes with temperature, the entropy of an ideal gas changes with pressure. So if the pressure increases, sure, that generally pushes the entropy to increase. But guess what? The pressure could change by increasing or decreasing and dwarfed the change in temperature effect. All right? So don't forget that last part that I circled in red. How about if you assume constant specific heats? Isn't that C sub V T2 minus T1? What about for H? C sub P T2 minus T1. How about the change in S? C sub P natural log of T2 over T1 minus R natural log of P2 over P1. True or false? So this is some little more analytic. I can work with equations a little longer. from state 1 to state 2 up to state 3. So this is T3 right there. Anytime you have a second law analysis, it's S2 minus S1 is equal to Q1 to 2 divided by TB. That's entropy coming in. And any generation 1 to 2. Second law for a process. True? Some people forgot this on the last exam. If there was any heat transfer coming in, then it's always going to bring in some entropy. It's divided by the boundary temperature that it comes in, okay? All right. Don't forget that term. So anyway, so it's not because of entropy generation that there's an increase in entropy. It's because of heat transfer in, because what is the entropy generation for 2 to 3? It's 0 because it's internally reversible. The air standard analysis, frictionless, internally reversible. True? Okay. So now from 3 down to 4, that was isentropic expansion, S equal to a constant, then 4 back to 1, V is equal to a constant. It's cooling. So if you wanted to, you could put in 2 to 3. Isn't that the Q in from 2 to 3? How about Q out? True? True. Let's do this. We identified, we could write the first law and the second law for each process. All right. If you go ahead and do that, you'll be like U2 minus U1 is equal to Q1 to 2 minus work 1 to 2. True? That's just the first law for the process 1 to 2. You just write it again. Q 3 minus U2 is equal to Q2 to 3 minus work 2 to 3, right? And then I'm going to run out of room. 4 minus U3 is equal to Q. 3 to 4 minus work 3 to 4. And then the last one, U1 minus U4 is equal to Q. 4 to 1 minus work 4 to 1. We should be able to write that first law and evaluate these terms for each process, and then also for the cycle. What is the Q net of the cycle? It's going to be the sum of all the Q's. The Q1 to 2 plus Q2 to 3 plus Q3 to 4 plus Q4 to 1, right? And then the work net is going to be work 1 to 2 plus work 2 to 3 plus work 3 to 4 plus work 4 to 1, right? Okay. Which of these 4 Q's are 0? That's right. The Q1 to 2 is 0. Why is it? It's isentropic. And the way they got it was insulated and reversible compression, meaning isentropic compression. How about the other Q? Which one? 3 to 4 is 0. And then 2 to 3, is that positive or negative? 2 to 3. It's positive in. And 4 to 1, it's negative. It's going out. So it's negative. Right? I show it out as a positive entity out, but if you're staying with our sign convention, Q4 to 1 is a negative. So many kilojoules per kilogram. Now let's do it for the work. Talk to me. There's 2 works that are non-zero and 2 works that are 0. Which 2 works are 0? Work 2 to 3 is 0 and 4 to 1 is 0. Why? How can you tell? On the PV diagram, there's no change in volume. Oh, there's a change in pressure, but you needed that integral f dx. I need a dx or I need a dv, an expansion or compression for boundary work. So let's talk about this one. Work 1 to 2, is that positive or negative? Is it into or out. If it's out, it's a positive work out. From 1 to 2. So it's a work in, so it's a negative work for our sign convention. And then our work 3 to 4, it's a positive. So when you calculate the Q's, you'll have two non-zeros. One will be negative, one will be positive. And you calculate the works, one will be negative, one will be positive. Let me ask this. If I do everything right, will Q net equal to W net? I heard a couple yeses and a couple no's. That means half the class is right, half the class is wrong. We hear a confident yes. And another confident yes. It's melting away the no's. Their confidence is catching. Which is it? Everybody should be able to answer that question in this class. It is yes. It is yes. Okay. What's the thermal efficiency defined as of this cycle? The work net out divided by Q in, which is not Q net, it's only Q 2 to 3. It's only when you put the heat in. Now, sometimes what you'll do is you'll show it as work out and then work in. What do you mean work in? Well, that's why we have those flywheels. It's going to take some mechanical energy for the compression stroke. You can work out the thermal efficiency for that Otto cycle, assuming constant specific heats. Gets to be just the thermal efficiency is 1 minus 1 over the compression ratio raised to the K minus 1. What is K? 1.4 C sub P over C sub V for cold air. Right? And if you plot that, you plot the thermal efficiency as a function of compression ratio for the Otto cycle. You start at 1, go to compression ratio of 2, 3. It's not going to work well with a compression ratio of 1, right? Let's see, that's ratio of volume bottom dead center to volume top dead center. You didn't have no volume change. 3, 4, 5, go out to about 10. And what you'll find is it'll go from 0 up. So increasing the compression ratio has a positive impact. Increasing R, the compression ratio, has a positive impact on thermal efficiency. It comes from this analytic expression. You want to see it derived? This is cheating. I point you to the website where I did it once before. And you just do a search on derivation of Otto cycle thermal efficiency. And there it is, and you can watch it. I can do it again if you want me to, but in the interest of time, how about I just let it go? Now let's solve a problem. Otto cycle, air standard analysis using variable specific heats. I really don't want to solve this problem. Not variable specific heats, constant specific heats for my solution. Let's do constant specific heats, okay? What you want to do is you want to make a sketch from your memory. I know it's in the textbook, but you really should get down the PV diagram and the TS diagram from memory, okay? And you want to go state 1 to 2 to 3 to 4, back again. And on a TS, 1 to 2 to 3 to 4, back again. 1 to 2 to 3 to 4. And then what you want to do is you probably want to make up a list of delta U's, Q's, and W's for each of the process. 1 to 2, 2 to 3, 3 to 4, 4 to 1. Just, you've got a table, and I know you have a table just of how does the internal energy change? How is the Q's, are they positive, or the 0, or the works, okay? And each of these kilojoules per kilogram, kilojoules per kilogram, kilojoules per kilogram, right? All right. Now, I can populate some of this table already. What is the Q 1 to 2? And this one, 0. Work, 2 to 3. then Q 3 to 4, then work 4 to 1. Those are all, I got some of those. Half of them are done, right? I did the easy half. You do the next half. All right, and then the other one is I like to remind myself, look at from work 1 to 2, this better be a negative answer I put in there. Otherwise, something's going wrong. And then work 3 to 4, that better be positive. And then when I sum it up, this better be a positive sum. If I sum this column right here, so that work net will be the sum of that column. Now, likewise, Q net, it'll be a positive number, and it'll be equal to work net. Otherwise, I've done something wrong. I need to look for my error. Okay, this Q 2 to 3 is positive in. And this is negative, so it's an out. All right. If I calculated all of these delta U's, if I sum those up, guess what that's equal to? This whole column. It better be 0. The changes in internal energies, just look at the sum. It's going to be 0. The other table that I want is for the state. All right, state 1, state 2, state 3, state 4. And the pressure in, what do they have it? Kilopascal. And the temperature in Kelvin. All right. All right. Let's populate this table first for the states. So at state 1, do they give me the pressure at 1? At the start of the compression stroke. So is this 300 Kelvin and 95 kilopascal? Right? Okay. The compression ratio is 9, so I want to store that information somewhere. R is equal to 9.5. Compression ratio 9.5. The maximum temperature of the cycle is 1100 K. Where is my maximum temperature? State 3. Glad I drew that TS diagram, right? So it's 1100 Kelvin. Now consider constant specific heats and make the calculation. I didn't give you the C sub V is 0.718 kilojoules per kilogram Kelvin, and the C sub P is 1.005 kilojoules per kilogram Kelvin. So what is the temperature at the end of the compression stroke? I'm looking to solve for T2. I'm going to run out of room, so I'll make the best that I can, but how do I find T2? Yes, so we know it's isentropic, and so constant specific heats, we can recall this ratio is right here. We'll use one of these equations, okay? Which equation will we use, A, B, or C? Well, let's take a look at the diagram. The pressure volume diagram is state 1, and we go to state 2, right? So what is my compression ratio? V1 divided by V2. Isn't that 9.5? Isn't that 9.5 the compression ratio? So I know the ratio of the volumes, right? So what was I asked to calculate? T2? B. So T2 is equal to T1 times V1 over V2. Hey, isn't that compression ratio R? To the 1.4 minus 1, which is 0.4, 0.4 as the exponent. Now, the next question probably is saying, calculate P2. Well, would I use equation A, B, or C to calculate P2? You could just go to P1 compression ratio to the K. So what was our, it's 9.5 for the compression ratio, and we started at a temperature of 300 Kelvin, 9.5 to the 0.4, and so we calculate that the temperature at state 2 is 738.3 Kelvin. And then this pressure, We started at 95 kilopascal, 9.5 to the 1.4 power, and we find the pressure is 2,221 kilopascal. You would save more digits in your calculator. Make sense? I could populate this table. It would say, oh, it's 2221. This is 738.2 or 738.3. How about the pressure at state 3? Well, they told me the temperature at 3. Look at this property diagram from 2 to 3. What's constant? Specific volume. Is it always an ideal gas such that P2 V2 divided by T2 is equal to P3 V3 divided by T3? And the volumes are the same? It's so if you wanted to calculate P3 is equal to P2 times T3 divided by T2, and the temperatures are known. And so you calculate that this jumps up to 3309 kilopascal. What about going from 3 to 4? It's very similar to 1 to 2, but you have not a compression ratio of 9.5, you have an expansion ratio, so 1 over 9.5. And you use the similar equation, so the pressure goes to 141.6 and 447 Kelvin. Now, this pressure is still above atmospheric pressure. So that discussion about the exhaust rushing out as soon as you crack open that valve. What happens here is from 4 to 1, it's a constant volume cooling. Okay, so how do I solve for the process 1 to 2? I've got the states. How do I solve for delta U? Isn't that C sub V T2 minus T1? Isn't that U2 minus U1? And you can put the answer in there. What about the work? How do I solve for the work 1 to 2? It's equal, because if you just look at the first law, I'm going to try and scoot it right over here. Delta U is equal to Q 1 to 2 minus work 1 to 2, right? This is 0, and so delta U is C sub V delta T, and so I can solve for work 1 to 2 is minus delta U, right? And so the work 1 to 2 comes in at negative 314.7 kilojoules per kilogram. How did I calculate that again? C sub V times delta T, T2 minus T1. Okay. Let's take a look at the second process. So we know that we need to calculate this positive Q, but what is delta? Is this going to be C sub V T3 minus T2? For delta U, U3 minus U2? And then the first law is U3 minus U2 equal to Q 2 to 3 minus work 2 to 3, and that work 2 to 3 is 0, right? And so Q 2 to 3 is simply U3 minus U2, and we calculate that, so this turns out to be 259.8 kilojoules per kilogram. Is it positive? Yes. Is it in? Yes. All right. Similarly, write for the third process, U4 minus U3 is equal to Q 3 to 4 minus work 3 to 4. We know that the Q is 0. And so we know how to calculate U4 minus U3, C sub V T4 minus T3. And then we have minus that gives us the work 2 to 3, which is a positive 468.9 kilojoules per kilogram. Let's continue on. So it's U1 minus U4 is equal to Q 4 to 1 minus work 4 to 1. So this is C sub V T1 minus T4. And we calculate a negative work. This work is 0, a negative heat transfer. And that Q 4 to 1 is negative 105.6. If you do the Q net, it's 154.2. Just sum them up in that column. If you do the work net, it's 154.2. They agree. I'm good. That's a good check, right? Check, check, check. So I haven't discovered an error. I forgot to keep mentioning the answer for part A, the temperature to end of the stroke, that's T2 right here. The peak pressure, what's the peak pressure? That's the pressure at 3. Whoops. This is the temperature at 2. Then the pressure at 3. What is the net heat addition for the cycle? Net heat in addition, that's only going to be the 250, get rid of this right here, 259.8 kilojoules per kilogram. That's what's in. And then the net work for the cycle, that's going to be the 154.2 kilojoules per kilogram. And so the thermal efficiency is the ratio of the net work, 154.2, divided by the heat in, 259.8. And the thermal efficiency for this ideal Otto cycle is a whopping 59.4%, very high. It's very high, but it's idealized. And so if you go back with this 9.5 compression ratio, you should be able to put into the equation, somebody have a calculator? Thermal efficiency is 1 minus 1 over R K minus 1. Put in 1 minus 1 over 9.5 to the 0.4. Somebody want to run that? And I think you'll get very close to 59.4%. 59.36. Otherwise we get an error, right? We have an error. We need to look for it. One other thing that John has been working with me on this summer is at a particular website that I control, engineering.utsa.edu. That's a tilde R and then my last name. He's about ready to let it, it's out there. You can access it. Anybody can access it, but I'm going to start pointing students to it such that we tried to organize per class, Thermo 1, Thermo 2, and then fluids per class by topics or lectures. Okay? So here, there's a whole bunch on exergy, whole bunch on vapor power cycles, Otto, diesel, and gas power cycles. And so that cold air standard Otto cycle example problem, and there's even a PDF file, so you can watch the video, it'll go to YouTube, or download the PDF file, work it, and if you get stuck or want to check your answer, then go look at the YouTube, right? And we're even thinking of adding another one called SOLN, which means you download a PDF of just the raw problem statement, work it, and then just download a PDF of the solution, check it, and if you're still lost, go watch the video as a last resort. So anyway, here I have it up and over here. No, that's actually, look at, I have the derivation of the Otto, the derivation of the Brayton, and the derivation of the diesel cycle, all done out there that you can look at from last time. Assuming cold air standards. All right. And this is that website that I showed you just now. But you can go check out Brayton cycle. Actually, it's really interesting. This introduction to the Brayton cycle, because at YouTube, I didn't encourage you to play too much with it, but it's funny. That's the most viewed video. Introduction to Brayton cycle is my most viewed video. I would have never guessed. It is not from UTSA students. There's a long list of students from all over, or wherever they're at. I don't know if they're come on, who's interested in learning this type of stuff? They're engineering students somewhere in the world. But it's consistent. It's been up. It's been the #1 video since I published it in 6 months, and I haven't So it's very interesting that it's number one still. So not very many. I mean, come on. Somebody puts a music video up and they have 2 million views in a couple of days, but I'll have to do this statistic, but it's over 25,000. And then my son, he's played around with it a little bit. He looked, he says, and I don't know how he did it, but he clicked on it. He says the total number of hours watched, he just jaw dropped. That many hours watched of your stuff, it's because these are long videos, right? They're like an hour. And it's like it's summed up to a long time. I forget what the statistic was. But anyway, give me your feedback on this. There's a bunch of stuff for those that are going to be taking Thermo 2 with me next semester, hopefully everybody here. But also you can check out lectures for Thermo 1 even. I've gotten them lined up as we've been doing it this summer. No topics because it's just too hard to make these. Coming soon. May never come. It may never come. But there's fluid mechanics as well, the lectures and fluids. There you go. So with that, I'm going to stop and we're going to talk about the exam.